time. It slips through our fingers with every heartbeat, carries us from birth to death, and binds every star and planet in its silent flow. It is the river that no one can escape, the unseen thread upon which every moment of existence is strung. Yet from the earliest myths to the most advanced equations of modern physics, humanity has asked the same forbidden question. What if the river of time could be defied? Could we step out of the present into the past? Could we leap ahead to glimpse futures yet unwritten? Could time itself be bent, twisted, or reversed? The thought has haunted kings and prophets, dreamers and scientists. Ancient myths spoke of gods who moved outside of time. Philosophers wondered if fate was fixed, if the future was already written. And in the age of machines, storytellers like H.G. Wells gave us visions of devices that could tear open the veil of years. But time travel is not only a dream. It lives at the edges of science, in the equations of Einstein, in the paradoxes of logic, in the strange experiments where clocks run at different speeds. It lives in black holes and wormholes, in the quantum shadows where certainty dissolves. The universe may not simply allow time travel, it may already be doing it. This is not just a story about physics. It is about longing, about the human refusal to accept limits, about the search for freedom from time's relentless grip. Tonight, we go in search of the truth. Is time travel an illusion of the imagination, or a reality written into the very fabric of the cosmos? The dream of escaping time. From the moment humans first looked upward at the sky, time revealed itself as both mystery and tyrant. The sun rose and fell, the moon waxed and waned, the stars wheeled overhead in patterns so precise they became calendars before they became constellations. Time gave order to life, planting and harvest, birth and death, the passage of generations. But time also imposed its cruelty. Nothing endured. The seasons repeated, but moments never returned. Children grew old. Empires collapsed. Memory was the only refuge against the relentless current of becoming and vanishing. This contradiction between the cycles of nature and the irretrievability of moments gave rise to myth. To the ancient Mesopotamians, comets and eclipses were not just astronomical events, but signs of destiny. They believed time was written in the heavens, that the gods measured kings and kingdoms in the rhythm of celestial bodies. To the Hindus, time itself was cyclical, not linear, a cosmic wheel turning through ages of creation, preservation, and destruction, only to begin again. 1,000 years in heaven might be but a day on earth, and so stories arose of mortals who visited higher realms and returned to find centuries had passed. In Greece, the god Kronos embodied time's inexorable power, devouring his children as if to devour the future itself. Yet the Greeks also imagined Kairos, the opportune moment, the slice of time where destiny could be seized. Their dual vision reflects humanity's tension with time, part fate, part opportunity, always beyond control. Philosophers soon took up the challenge of defining the indefinable. Heraclitus famously declared that one cannot step into the same river twice. Everything flows, everything changes. Aristotle tried to pin it down more clearly. Time, he argued, is the measure of motion, inseparable from change in the physical world. And then came the more haunting voices. In his Confessions, St. Augustine asked what time truly was. If no one asks me, I know. If I try to explain, I do not for him. The past lived only in memory, the future only in expectation, the present only in a fleeting instant that vanished as soon as it arrived. Time was both undeniable and elusive, something felt something lived, yet impossible to hold. Across civilizations, one desire was constant: to escape the burden of time. In myths, gods stepped outside of it, dwelling in eternity. Heroes longed to return to the past, to undo mistakes, to seize the lost. Prophets dreamed of visions of the future, believing fate was already written. These stories, scattered across cultures, reveal not superstition, but psychology. Humanity's relationship with time has always been one of awe and rebellion. To imagine controlling time was to imagine controlling destiny itself. As centuries passed, the mythic and philosophical visions of time began to give way to something new: imagination powered by science. The Industrial Revolution reshaped life, filling it with machines, gears, locomotives, and engines. Human beings no longer lived only by the cycles of the sun and stars. They now lived by the relentless ticking of clocks. Time became something quantified, regulated, commodified. And in this age of machines, the dream of escaping time evolved too. It was here that literature seized the question with new force. In 1895, H.G. Wells published The Time Machine, and with it, he transformed an ancient longing into a modern vision. Wells's protagonist did not rely on magic, gods, or myth. He built a machine, a contraption of brass and ivory, capable of moving through the fourth dimension just as easily as a train moves through space. Time became a landscape to be traversed, with past and future as destinations, not abstractions. The novel was a revolution in thought, suggesting that time was not only something endured, but something navigable. Other writers followed. Jules Verne, though more grounded in plausible engineering, touched upon similar themes of future and past. In the 20th century, as cinema emerged, time travel became a staple of storytelling. Films like Back to the Future, The Terminator, and Looper gave visual life to paradoxes that philosophers had debated for centuries. Could the past be changed? Could the future be avoided? Could one event ripple endlessly through history? These stories gripped audiences not only because they were thrilling, but because they touched something universal. To long for time travel is to long for mastery over regret. Everyone has moments they wish to undo, words they wish they had spoken or not spoken, opportunities missed, tragedies endured. In the human heart, time travel represents the ultimate form of healing. It promises redemption, the chance to fix what was broken, to restore what was lost. At the same time, it also embodies humanity's restless curiosity about the future. What lies ahead for us, for civilization, for Earth itself? If the veil could be lifted, if we could peer centuries ahead, would we see hope or despair, progress or ruin? Time travel stories, then, are not escapism alone. They are mirrors of the deepest anxieties and hopes we carry. They reveal our obsession with control, our unease with fate, and our refusal to accept that time's flow is irreversible. And they prepare us, in a strange way, for the moment when science itself enters the conversation. Because in the 20th century, it did. With Einstein's theories, time was no longer absolute. It was not a universal clock ticking evenly for all. It bent, stretched, and folded under the weight of mass and the speed of motion. Suddenly, the dream of time travel shifted again. It was no longer the territory of myth and fiction alone. It was written into the fabric of reality itself. The river of time might not be as unyielding as we once thought. And so, from myth to philosophy to imagination, the dream of escaping time sharpened into a scientific question. Could time be traversed like space? Could the past be revisited, or the future reached before its arrival? What once belonged to gods and storytellers now belonged also to physicists, astronomers, and mathematicians. Humanity's rebellion against time was no longer only longing, it was investigation. This is the legacy of the dream, a lineage stretching from ancient myths of eternity, through Augustine's restless paradoxes, through Wells's shining machine, to the laboratories and observatories of the present. The desire has not changed. What has changed is the language, from prayer and poetry to mathematics and equations. And in that shift lies the beginning of our journey into the truth of time travel, not only as myth, but as reality, Einstein's revolution. At the turn of the 20th century, the universe seemed predictable. For more than 2 centuries, Isaac Newton's laws had ruled the cosmos like scripture. Time was absolute, a perfect clock ticking uniformly for all observers. Whether a stone fell on Earth, a planet circled the sun, or a comet streaked through space, the laws of mechanics applied equally, and time was the impartial backdrop against which all events unfolded. The idea was comforting in its simplicity. Past, present, and future existed on a single timeline, flowing steadily forward, the same everywhere in the universe. But as the 19th century drew to a close, cracks began to appear in this neat mechanical order. Experiments with light revealed puzzles that Newtonian physics could not solve. The speed of light, measured again and again, appeared to be constant, unchanging no matter how fast the observer moved. According to Newton, this should not have been possible. Velocities were supposed to add and subtract like numbers. If one ran toward a moving cart, its speed relative to the runner changed. Why should light, moving faster than anything else, remain the same for all? It was in this climate of uncertainty that a quiet patent clerk in Bern, Switzerland, began to reimagine the universe. Albert Einstein, in 1905, published his paper on special relativity, and with it shattered the very foundation of absolute time. His insight was radical. There is no universal clock. Time flows differently for different observers, depending on their speed. If 2 people move relative to one another, their measurements of time will not agree. Time itself becomes relative, woven inseparably with space into a single fabric called space-time. The implications were profound. A moving clock runs slower than a stationary one. A fast-moving traveler ages less than one who stays behind. Time, once thought of as a rigid container, revealed itself to be elastic, stretching and contracting under the influence of motion. Suddenly, the dream of time travel was no longer myth or fiction. It was a natural consequence of the way the universe truly works. The first confirmation came not from science fiction, but from physics itself. Einstein predicted that time dilation would be real, measurable, and testable. And though early experiments were crude, later technology would prove him right beyond doubt. Astronauts in orbit, moving at tremendous speeds relative to Earth, experience time slightly slower. Precise atomic clocks flown on airplanes return fractions of a second, younger than those that remained on the ground. Even the GPS satellites above our heads must account for time dilation in their programming, adjusting their onboard clocks so that they remain synchronized with Earth. Without relativity, navigation itself would fail. Einstein's revolution did not stop with motion. In 1915, with general relativity, he expanded his ideas to include gravity. Here, space-time was not merely flexible, but dynamic, curving in the presence of mass and energy. Planets orbit the sun not because of an invisible force pulling them, but because the sun bends space-time itself, guiding their paths. And with this insight came another radical truth. Time itself is slowed by gravity. A clock on Earth's surface, deep within the gravitational well, ticks more slowly than a clock far above in orbit. Time bends under the weight of matter. To Einstein, this was more than equations. It was a glimpse into the profound strangeness of reality. If time was relative, then the universe was not the orderly, absolute clockwork of Newton, but something far stranger. Past, present, and future were not universal truths. They were perspectives dependent on position, velocity, and gravity. Reality itself was no longer singular, but multiple, each observer experiencing their own version of time. And so, at the dawn of the 20th century, the dream of time travel found its first foothold in real science. No longer confined to myth or novels, it became part of physics itself. The laws of the universe, once thought unyielding, revealed a loophole. That time is not a single flow, but a landscape that bends, stretches, and slows. For the first time, the possibility of escaping time's tyranny had a mathematical foundation. The true measure of a theory is not in the elegance of its equations, but in the weight of its evidence. For Einstein's relativity, the first great test came in 1919, during a solar eclipse that turned the world's gaze to the sky. According to general relativity, the sun's immense gravity should bend the light of stars passing near its edge. If true, the positions of those stars would appear shifted when viewed during an eclipse. Astronomer Arthur Eddington led an expedition to measure the effect, and when the results were announced, they confirmed Einstein's prediction. Headlines declared that Newton's universe had been overturned. Time and space were no longer rigid. They were elastic, curved by gravity itself. This was more than a scientific milestone. It was a cultural earthquake. For centuries, the laws of Newton had been synonymous with certainty. Now they were shown to be approximations, shadows of a deeper truth. Time, once the ultimate constant, had become dynamic, relative, and strange. The world was forced to confront the fact that reality was far less stable than once imagined. The evidence continued to grow. Astronomers measured the slowing of clocks in gravitational fields. Physicists observed time dilation in high-speed particles, whose lifetimes stretched far beyond expectation. Later, as technology advanced, experiments became exquisitely precise. In 1971, atomic clocks flown on airplanes around the world confirmed both gravitational and velocity-based time dilation, matching Einstein's predictions to extraordinary accuracy. Today, satellites in orbit must adjust their clocks for these relativistic effects, or else GPS would drift by kilometers each day. The strange bending of time is not only real, it is a part of everyday technology. Einstein's insights also opened the door to phenomena once thought unthinkable. If space-time could bend, what happened when the bending became extreme? The equations of relativity predicted regions where time slowed nearly to a halt. Black holes, cosmic abysses where gravity became so strong that not even light could escape. In their presence, time itself behaved differently. For an outside observer, an object falling into a black hole would appear frozen, its descent slowed infinitely. Within, time would collapse toward a singularity, a point beyond which physics itself breaks. These were no longer mythic visions of eternity. They were the real consequences of the universe's laws. Relativity also hinted at possibilities far stranger than black holes. If space-time was a fabric, could it be folded? Could two distant points be bridged by a tunnel, a wormhole, that linked them across vast distances and perhaps across time? The mathematics suggested that such passages were possible, at least in theory. They required exotic matter, negative energy, conditions far beyond our current engineering, but the seed of the idea was there. Time was not only relative, it might be navigable, twisted, perhaps even traveled. By the middle of the 20th century, relativity had transformed the dream of time travel into something more than fantasy. It gave the dream a framework, a set of equations that did not forbid it outright. Instead of declaring time immutable, relativity revealed its malleability. The question was no longer, is time travel possible, but how far can the fabric of space-time be stretched before it tears? And yet, beneath the exhilaration lay unease. If time was not absolute, then past, present, and future could not be universal. Each observer carried their own version of time, stitched to their path through space. The notion of a single, shared now dissolved. The cosmos became a mosaic of perspectives, each valid, none supreme. Einstein's revolution was not just a scientific shift, but a philosophical one, forcing humanity to see reality itself as relative. Thus, from a patent clerk's thought, experiments emerged a universe stranger than myth. Time was no longer a river flowing evenly from past to future. It was a landscape, curved and stretched, where clocks disagreed and gravity sculpted duration. And in that landscape, the first scientific footholds for time travel had been found. Not in fantasy, but in the mathematics of reality itself. Time dilation in practice. Time dilation is no longer confined to Einstein's equations or abstract thought experiments. It is a phenomenon we can measure, observe, and even experience in our everyday world. The bending of time is not only real, it is essential to how we navigate, travel, and even understand our place in the universe. The first hints came from the simplest of thought experiments. Imagine two identical twins. One remains on Earth, while the other boards a spacecraft traveling at speeds close to that of light. When the traveler returns, less time will have passed for them than for the sibling who stayed behind. The twin paradox, as it became known, was not a contradiction, but a consequence of relativity. Motion itself alters the flow of time. The faster one moves, the slower their clock ticks compared to those at rest. For decades, this remained a thought experiment, an elegant possibility without proof. But as technology advanced, the cosmos revealed that time dilation everywhere. Consider the lives of particles called muons. These unstable subatomic particles are created in Earth's upper atmosphere when cosmic rays strike molecules of air. In the laboratory, muons decay in millionths of a second. By Newtonian physics, they should never reach the ground. Yet they do. Why? Because they are moving so fast that, from Earth's perspective, their clocks slow down. Their brief lifetimes stretch long enough for them to penetrate deep into the atmosphere, where detectors can measure them. Without time dilation, they would vanish almost instantly. Later, physicists put Einstein to the test with clocks. In 1971, Joseph Haffel and Richard Keating carried 4 atomic clocks aboard commercial airliners around the world. One set traveled eastward, the other westward, while reference clocks remained at the U.S. Naval Observatory. When the airborne clocks were compared with the stationary ones, the results matched relativity. They had ticked at different rates, their times shifted by the motion of the planes and the pull of gravity. The differences were tiny, mere billionths of a second, but measurable, undeniable. And then there are astronauts. Aboard the International Space Station, astronauts circle Earth at more than 28,000 kilometers per hour. Their speed causes their time to run slightly slower than that of people on the ground. But at the same time, they are farther from Earth's gravity, where time runs faster. The two effects nearly cancel each other, but not entirely. Over the course of 6 months in orbit, an astronaut may return to Earth milliseconds younger than if they had stayed behind. It is not science fiction. It is measurable, lived experience, human beings becoming, in a small but real way, time travelers. Yet the most striking example of time dilation hides not in experiments, but in the devices we use every day. The Global Positioning System, GPS, relies on satellites orbiting Earth, each carrying atomic clocks. Those satellites experience both effects of relativity. They are moving fast, which slows their clocks, and they are farther from Earth's gravity, which speeds them up. The combined effect is a difference of about 38 microseconds per day. If uncorrected, GPS would accumulate errors of several kilometers each day, rendering navigation useless. Instead, the system constantly accounts for relativity. Without Einstein, the maps in our phones would fail. Time travel, in this sense, guides us to our destinations every day. Thus, time dilation is not myth, nor even just theory. It is woven into the very fabric of modern life. It is proof that time is not fixed, not absolute, but a shifting landscape shaped by speed and gravity. Each plane that flies, each particle that decays, each astronaut who orbits is a reminder that we already live in a universe where time travel is real, though subtle, measured not in years but in milliseconds. If the gentle differences of time dilation on Earth and in orbit already shape our daily lives, the extremes of the universe reveal its most profound possibilities. For here, near the speed of light, and in the crushing grip of gravity, time dilation ceases to be a curiosity and becomes a pathway into the future itself. Imagine a spacecraft capable of approaching the speed of light. At 90% of light speed, time aboard would pass at less than half the rate compared to Earth. At 99%, days inside the ship might equal years for those left behind. Push closer still to 99.999%, and the gap becomes astonishing. A single year of travel could equal centuries on Earth. This is not imagination, but mathematics, the inescapable outcome of relativity. Though technology cannot yet accelerate us to such velocities, the equations reveal what awaits. Journeys where explorers return to find civilizations changed beyond recognition, where travelers move into the far future while experiencing only brief spans themselves. The same phenomenon emerges in the warped depths of gravity. Near a black hole, space-time bends so steeply that time for a distant observer and time for one near the event horizon become radically different. To hover at the edge of such an abyss is to see the universe outside race forward, while your own seconds stretch long and slow. The film Interstellar famously dramatized this with the planet near a black hole, where 1 hour equaled 7 years outside. While dramatized, the concept rests firmly in relativity's truths. Extreme gravity can transform minutes into decades, making black holes natural time machines, one-way journeys into the future. Already, the universe provides demonstrations. Pulsars, spinning remnants of massive stars, act as cosmic clocks, their pulses precise to millionths of a second. When observed near other massive objects, their timing shifts, distorted by gravitational time dilation. Astronomers use these variations to test relativity, and again, Einstein is proven right. Time does not flow evenly across the cosmos. It bends, stretches, and slows, sculpted by matter and motion. Yet perhaps the most haunting implication is this: the future is already written into the fabric of relativity. A traveler who ventures near a black hole or accelerates close to light speed will not leap into the unknown, but into a future already present in spacetime's geometry. Time travel to the past remains elusive, tangled in paradox. But travel into the future is not forbidden. It is inevitable, if only we find the means. The irony is that we are already time travelers. Every step forward is a journey into the future. Each second carries us farther from the past, guided by relativity's subtle hand. Astronauts, pilots, even the satellites above us, all experience it, however minutely. It is the promise that one day, perhaps, humanity will harness this truth not only to measure, but to explore, to sail the rivers of time as surely as we sail the seas. Dilation shows us that time is not uniform, not absolute, not beyond influence. It is malleable, sculpted by speed and gravity, a fabric to be bent rather than a chain to endure. And in that truth lies the first genuine path to time travel. Not in myth, not in fiction, but in the physics of the universe itself, the arrow of time. Time does not simply pass. It flows, carrying us from one moment to the next, always forward, never back. A glass shatters on the floor, but never leaps whole again into the hand. Smoke drifts from a candle into the air, but never reassembles into wax and wick. A child grows into an adult, but never the reverse. In every corner of experience, we feel the same truth. Time has a direction. It is the arrow that flies one way only, pointing toward the future. Yet this direction is not written in the equations of physics. The laws that govern the dance of particles are reversible. Whether a planet circles clockwise or counterclockwise, whether molecules collide forward or backward, the mathematics holds true. Nothing in Newton's mechanics or even Einstein's relativity requires time to flow one way. And yet, in the lived world, it does. The question is why? The answer lies in the heart of thermodynamics, in the law that governs order and disorder, entropy. The second law of thermodynamics declares that in a closed system, entropy, the measure of disorder, can only increase. Heat flows from hot to cold, not the reverse. Energy spreads, gradients dissolve, structures decay. This law gives time its arrow. A pristine glass can shatter into pieces because there are vastly more ways for shards to lie on the floor than for molecules to hold together in fragile perfection. A child becomes older because biological processes, driven by chemical reactions, move toward equilibrium, not away from it. Entropy gives us the flow from past to future. The past is the state of lower entropy, more ordered, more improbable. The future is the drift into higher entropy, more chaotic, more likely. Each moment, then, is the accumulation of chance, the unfolding of disorder. The arrow of time is not a mystical current. It is the statistical inevitability of systems seeking balance. And yet, this explanation carries an unsettling implication. If entropy is the foundation of time's arrow, then time's direction is not absolute but emergent. It is not a law written into the universe's core, but a consequence of its initial conditions. The Big Bang, in its birth of unimaginable order, set the arrow in motion. The universe began in improbably low entropy, and from that improbable beginning, all disorder has flowed. Without that starting point, the arrow might not exist at all. Here, then, lies the paradox. The laws of physics are symmetric, but the universe is not. The equations allow time to run forward or backward equally, but the cosmos itself has chosen one path. We live inside that choice, carried forward by the arrow, unable to return. Time is not simply measured in clocks or in Einstein's elastic fabric. It is felt in the shattering, the fading, the decay. It is lived in the irreversible. And so, before we can imagine bending time or traveling through it, we must understand its nature. Why does it flow? Why does it not reverse? What is the arrow that defines our existence? These are not abstract questions. They are the ground upon which every speculation about time travel must stand. For if time's direction is only a byproduct, perhaps it could be challenged. Perhaps its arrow is not as unyielding as it seems. Entropy is the storyteller of the universe. It writes its narrative not in words, but in the slow unraveling of order, in the drift from the improbable to the inevitable. Every moment we live is a testimony to this law, and every breath we take is both an act of resistance and submission to it. But what does the arrow of time, anchored in entropy, mean for the cosmos itself? And what does it reveal about the possibility, or impossibility, of time travel? At the largest scales, entropy defines the fate of stars, galaxies, and the universe itself. A star burns because it transforms ordered hydrogen into the chaos of heavier elements and radiation. A galaxy evolves because gravity clumps matter into structures that then dissolve into radiant heat. Everywhere, the same process unfolds. Order exchanged for disorder, structure surrendered to equilibrium. Entropy does not only govern broken glasses and cooling coffee cups. It governs the life and death of worlds. The ultimate projection of this law is chilling, the heat death of the universe. In this far-off future, stars will exhaust their fuel, black holes will evaporate, and matter itself will decay into radiation. The cosmos will reach maximum entropy, a state of perfect disorder where nothing new can form, no structures can emerge, no differences remain. It will be a universe of stillness, without contrast, without time. For time is not merely measured by clocks, it is measured by change. When change ceases, the arrow of time loses its meaning. But the story may not be so simple. Some physicists wonder whether entropy is truly absolute, or if conditions might exist where the arrow could reverse. In certain interpretations of cosmology, the expansion of the universe may not continue forever. If it were to collapse in a big crunch, entropy could, in theory, decrease, and time itself could run backward. Such visions are speculative, uncertain, but they reveal the fragility of our assumptions. The arrow of time, so absolute in daily life, may not be fundamental after all. Even in quantum mechanics, hints of reversibility persist. The equations of quantum theory, like those of relativity, are time-symmetric. They allow for processes to run forward or backward. It is only when probabilities collapse, when measurements fix outcomes, that irreversibility seems to emerge. Some interpretations suggest that what we call the arrow of time may be a consequence not of the universe's laws, but of our perspective within them. We, as beings who remember the past but not the future, impose a direction where the underlying reality may be neutral. This raises unsettling possibilities. If entropy is the architect of time's arrow, and entropy itself is contingent, then time may not be an inviolable current, but a contingent flow. What we perceive as irreversible may, under different conditions, reveal itself as malleable. The dream of traveling backward in time, the forbidden desire to rewrite history, remains tangled in paradox. But forward time travel, already permitted by relativity, gains another layer of legitimacy. The arrow, after all, is not a wall, but a slope. To climb it may be difficult, but to slide down it into the future is inevitable. For humanity, the arrow of time carries both burden and beauty. It is what makes loss permanent, but it is also what makes growth possible. Without entropy, without the forward surge into disorder, there would be no stars to shine, no planets to form, no lives to unfold. The arrow that denies us reversal is also the arrow that creates the very stage upon which existence plays. And so, when we ask whether time travel is myth or reality, we must reckon with entropy. It reminds us that the flow of time is not an abstract dimension, but a lived truth, rooted in the physics of decay and change. It reminds us that the future is not simply ahead, but is carved by the irreversible march of disorder. And it whispers that the past, though mathematically conceivable, may be forever closed, not by paradox alone, but by the very nature of the universe itself. The arrow of time is not just a physical law. It is the condition of experience, the essence of mortality, the guarantee of impermanence. It is what makes the dream of time travel so haunting, because it asks not merely to visit another moment, but to defy the most fundamental truth we know, that all things fall apart and never return the same. Paradoxes and loops. If relativity bends time, and if the universe's equations do not forbid traveling through it, then a new challenge emerges, not from physics, but from logic. For when imagination takes us backward into the past, we collide with puzzles that seem to break causality itself. These are the paradoxes of time travel, and they reveal why the dream of reversing the arrow of time is so fraught with contradiction. The most famous of these is the grandfather paradox. It asks, what happens if a traveler journeys into the past and prevents their own ancestor from living, say, by stopping their grandfather from meeting their grandmother? The traveler's existence would be erased. But if the traveler does not exist, then they cannot journey into the past to change it. The act destroys the cause that made it possible. This loop is not only confusing, it seems impossible. The paradox sits at the heart of all. Backward time travel. If one can alter the past, one risks unraveling the very conditions that allowed the journey. Then there is the bootstrap paradox, sometimes called the causal loop. In this puzzle, an object or piece of knowledge is sent back in time, but its origin disappears. A traveler brings Shakespeare's Hamlet from the future to the past, and Shakespeare publishes it. Centuries later, the traveler finds the book and carries it back again. Who, then, wrote the play? No one. It exists in a loop without an origin. This paradox raises questions not only of causality, but of creation itself. Can information exist without a source? Can an object be real without ever being made? Science fiction thrives on such puzzles. Films, novels, and series construct elaborate loops. Heroes racing to prevent events that their very actions cause. Villains undone by their own interference. Timelines folding back upon themselves. Yet beneath the entertainment lies a genuine question. Can the universe allow such contradictions? Or does some hidden law, yet undiscovered, prevent them? Physicists wrestle with this seriously. One possibility is that time travel to the past is simply impossible. Nature forbids it, however much the equations of relativity tempt us. Another possibility is subtler, that paradoxes are resolved not by forbidding travel, but by limiting what travelers can do. This is the essence of the Novikov self-consistency principle, which suggests that any actions taken by a time traveler were always part of history. If you go back to meet your grandfather, you cannot prevent your own existence because the universe will conspire to keep events consistent. In this view, the past is fixed, unchangeable, even if visited. But such principles raise their own unsettling truths. If the past cannot be changed, then free will itself comes into question. A traveler's choices would be illusions, their every action already woven into history. To travel backward would be not liberation, but imprisonment, a tour through events that can never be altered. The paradoxes dissolve, but at the cost of freedom. And yet, another possibility looms. Perhaps paradoxes vanish not by consistency, but by divergence. In this scenario, a traveler who alters the past does not rewrite their own timeline, but creates a new one. The grandfather is prevented from meeting the grandmother, but instead of erasing the traveler, this act births a new branch of reality where the traveler was never born. Meanwhile, the traveler's original history remains intact, sealed in its own branch. This is the multiverse approach, rooted in interpretations of quantum mechanics. In such a cosmos, paradoxes do not exist because every possible history exists. A traveler may alter one, but infinite others unfold alongside it. Thus, the paradoxes of time travel are not idle puzzles. They are windows into the deepest questions of causality, free will, and reality itself. If backward, time travel is ever to be real, the universe must answer, is history fixed? Is it branching? Or is it forever closed, its doors barred by the contradictions within? The paradoxes of time travel are not only logical puzzles, they are mirrors reflecting our deepest uncertainties about causality and reality. To explore them is to stand at the edge of physics and philosophy, where imagination collides with the boundaries of possibility. One of the most vivid thought experiments is the Polchinski paradox, named after physicist Joseph Polchinski. Imagine a billiard ball entering a wormhole and emerging in the past, striking its earlier self in such a way that it prevents itself from ever entering the wormhole. The scenario produces an immediate contradiction. If the ball prevents its younger self from entering, then it cannot travel back to strike itself. But if it never travels back, nothing prevents it from entering. The loop spins endlessly between possibilities, unable to resolve. Yet Polchinski himself proposed a way out. Perhaps the ball can strike itself, but only in a way that nudges it into the wormhole with slightly different conditions. In this view, self-consistency reigns. The paradox dissolves, not because backward time travel is impossible, but because the universe forbids contradictions. Whatever happens is always what was meant to happen. This principle, the Novikov self-consistency principle, suggests that the past cannot be changed, only fulfilled. If you attempt to prevent an event, your actions will become the very cause of it. The loop closes neatly, without contradiction. It is a chilling vision of reality. Free will becomes illusion, and history becomes unbreakable. Time travel does not allow rewriting, only reliving. But there is another way the paradoxes might resolve, through the multiverse. If the universe contains not one timeline, but many, then traveling to the past may not alter your own history, but instead generate a new one. Kill your grandfather, and you do not erase yourself. You only create a branch where you were never born, while your original history remains intact. This idea finds echoes in the many worlds interpretation of quantum mechanics, where every quantum event splits reality into branches, each containing a different outcome. Time travel, in such a cosmos, becomes not a threat to causality, but a migration into another strand of possibility. Physicists remain divided. Some insist that paradoxes prove backward time travel is impossible. Others argue that physics may allow it, but with strict limits. Still others see in the paradoxes an invitation to rethink what we mean by time, cause, and reality. Are we bound by a single history? Or are we embedded in a network of countless histories, each branching and reconnecting like threads in a cosmic tapestry? Even our language falters in the face of these puzzles. To change the past implies that it exists as a fixed state, waiting to be rewritten. But what if the past, like the future, is simply a perspective? To travel backward may not mean altering what was, but experiencing a region of space-time from a new vantage point. The paradoxes may dissolve not through multiverses or consistency principles, but by recognizing that time itself is not what we imagine. Science fiction thrives in this ambiguity. From Back to the Future's vanishing family photos to Doctor Who's fixed points in time, the paradoxes fuel storytelling precisely because they dramatize our deepest desires and fears, to undo mistakes, to rewrite history, to escape regret. Yet physics forces us to confront whether such longings can ever be satisfied. If paradoxes reveal anything, it is that the universe may be stranger, stricter, or more generous than we dare to believe. And so, the paradoxes of time travel are not dead ends. They are gateways. Each contradiction is a challenge to our assumptions. Each loop forces us to re-examine what we mean by cause, effect, and freedom. Whether they forbid backward travel, demand consistency, or reveal branching worlds, they push us deeper into the mystery. Perhaps, in the end, the paradoxes are not warnings against time travel, but hints of its true nature. They may be telling us that the past is not as simple as we think, that causality is not linear, that reality is broader than one history. They may be, in their confounding beauty, the first signs that time travel, if real, will not be the dream we imagined, but something far stranger. Wormholes and gateways. If time dilation proves that time is flexible, then wormholes suggest something even more audacious, that time and space may be traversable. For within the equations of Einstein's general relativity lies a strange possibility, that space-time itself can form tunnels, shortcuts linking two distant regions of the cosmos. These are Einstein-Rosen bridges, better known as wormholes. The concept first emerged in 1935, when Einstein and Nathan Rosen sought to describe how two solutions to general relativity might connect. They imagined space-time as a folded sheet, where 2 points could be joined by a tunnel, like a bridge between valleys. To an observer traveling through the tunnel, the distance between the 2 points would collapse. What might take light years across ordinary space could, in principle, take minutes. Though breathtaking, the early vision of wormholes was fragile. The Einstein-Rosen bridge was unstable, collapsing instantly under its own gravity. A traveler attempting to pass through would be crushed before reaching the other side. For decades, wormholes lived more in speculation than in serious physics. They appeared in science fiction as shimmering gateways or cosmic doors, but in the mathematics of relativity, they seemed inhospitable. That began to change in the late 20th century. Physicist Kip Thorne, working with Michael Morris and Ulvi Yurtsever, explored whether exotic forms of matter, substances with negative energy density, could hold wormholes open. Their calculations suggested that, with the right conditions, a traversable wormhole could be stabilized, preventing collapse. It was an idea as radical as it was precise. Relativity did not forbid wormholes. It only demanded resources unlike anything we had yet harnessed. The implications for time travel were immediate. If one mouth of a wormhole could be moved at high speed or placed near a massive gravitational field, time dilation would cause clocks at the two ends to fall out of sync. Step into one mouth, and you might emerge not only in another place, but in another time, minutes earlier, centuries later, perhaps even in your own past. The mathematics allowed for it. The question was whether the universe did. Even here, paradox looms. A wormhole time machine risks creating closed time-like curves, paths through space-time that loop back on themselves. Such curves could permit paradoxes of the kind we explored earlier, where cause and effect dissolve into circularity. Some physicists argue that quantum effects may prevent such loops from forming, enforcing chronology like a cosmic censor. Others suggest that if wormholes exist, the universe may tolerate such strangeness, even at the expense of our common-sense notions of causality. Still, the dream persists. A wormhole offers not only escape from distance, but escape from time's tyranny. It would be a gateway, a literal hole in the fabric of space-time, through which the arrow of time itself could bend. And while no wormhole has yet been observed, and exotic matter remains theoretical, the very fact that relativity allows the possibility ensures that humanity will never stop searching. To peer into the equations and glimpse wormholes is to glimpse the universe's invitation, that reality may be stranger than we imagine, and that the paths through time may lie hidden in the folds of space itself. Wormholes stand at the edge of physics, not forbidden, yet not confirmed, shimmering in that liminal space between mathematics and reality. To understand them is to walk a tightrope between theory and speculation, grounded in equations yet reaching toward visions of gateways through space-time itself. At the heart of the problem lies stability. The classic Einstein-Rosen bridge collapses almost as soon as it forms, pinching shut before light, let alone matter, can pass through. To hold a wormhole open requires a peculiar ingredient: exotic matter. Unlike ordinary matter, which carries positive energy density, exotic matter would need negative energy, something that bends space-time in the opposite direction, counteracting the collapse. This idea may sound fantastical, but quantum theory whispers hints of its plausibility. In the Casimir effect, two uncharged metal plates placed close together in a vacuum experience an attractive force born from the quantum fluctuations of empty space itself. The energy, density between the plates is lower than that outside, mimicking a form of negative energy. Though tiny, this phenomenon proves that the vacuum is not empty, but alive with possibilities. If such effects could be magnified, perhaps they could provide the exotic matter needed to stabilize a wormhole. But even if stability were possible, new problems arise. Wormholes that allow time travel risk generating closed time-like curves, loops in space-time where an object could circle back to its own past. Such curves threaten causality, reviving the paradoxes we explored earlier. To some physicists, this is reason enough to doubt wormholes can ever serve as time machines. To others, it is evidence that nature itself may enforce a kind of chronology protection, a cosmic safeguard that prevents contradictions. Stephen Hawking famously suggested that quantum fluctuations near a wormhole's throat would destabilize it before paradoxes could occur. Yet research presses on. Wormholes are no longer confined to science fiction. They appear in serious theoretical work, in models of quantum gravity, and in discussions of black hole physics. Some even speculate that entanglement, the mysterious quantum link between particles, may be related to wormholes, as suggested by the bold ER equals EPR conjecture. If true, it would mean that wormholes and quantum connections are two faces of the same reality, binding distant points in space and perhaps in time. For culture, wormholes have become the visual metaphor of time travel. From contact to interstellar, they represent the possibility that space is not a barrier, but a bridge. In these depictions, travelers are swallowed by tunnels of light, hurled across the galaxy, spat out into other times. While artistic, these visions are rooted in genuine questions. The mathematics allows such tunnels. The physics of exotic matter hints at their feasibility. The only barrier is proof and technology. Thus, wormholes occupy a peculiar place in our imagination and science alike. They are not merely shortcuts through space, but doorways through time, promising the possibility of escaping both distance and duration. They remind us that the universe's fabric is not rigid, but pliable, capable of folds and twists beyond common sense. They may never be built, never be entered, never be more than theory. Yet the fact that they are not forbidden, that the laws of relativity permit them, ensures they remain one of the most tantalizing gateways in the human dream of time travel. Cosmic strings and exotic physics. The dream of time travel does not rest solely on wormholes. Relativity's equations and the strange imagination of theoretical physics hint at other mechanisms, paths through space-time that twist causality into unfamiliar shapes. Among the most fascinating are cosmic strings and other exotic constructs of the universe, relics that, if real, might serve as natural engines of time itself. Cosmic strings are hypothetical structures born in the earliest moments after the Big Bang. As the universe cooled and fundamental forces separated, some theories suggest that imperfections in the fabric of space-time may have formed. These imperfections would be unimaginably thin, thinner than a proton, yet stretch across the cosmos with densities so extreme that a single mile of string could outweigh the Earth. They are not strings of matter as we know it, but lines of pure energy, scars left behind in space-time's primordial weave. What makes cosmic strings so extraordinary is not just their density, but their geometry. A string would warp space-time around it, creating a conical distortion. Traveling around a cosmic string, one could take a shortcut, as if a wedge of reality itself had been removed. This distortion, when combined with motion, offers strange possibilities. Two parallel strings rushing past each other at nearly the speed of light could in theory create closed time-like curves, loops through space-time that might permit backward travel. In such a scenario, time would bend into a circle, allowing a traveler to re-emerge at their own past. The equations allow it, but the consequences are dizzying. Just as with wormholes, paradoxes lurk in every loop. And yet, cosmic strings remain tantalizing because they are not inventions of fiction alone. They emerge naturally from certain grand unified theories of physics. If they exist, they could be remnants of the universe's earliest phase transitions, stretched across billions of light years. Their gravitational pull might lens light from distant galaxies, producing observational signatures we could detect. Astronomers have searched for these distortions, scanning the sky for double images or peculiar arcs that could betray their presence. So far, none have been found, but the search continues. Cosmic strings are not alone in their speculation. Other solutions to Einstein's equations suggest rotating universes or Tipler cylinders, immense constructs that twist space-time into loops. The Tipler cylinder, proposed by Frank Tipler, imagines an infinitely long, massively dense rotating cylinder. Space-time around such a structure would spiral, dragging light and matter into closed time-like paths. In principle, a spacecraft navigating such spirals could return to its own past. But the catch is as daunting as the vision. An infinitely long cylinder cannot exist in our universe, and even finite versions would demand materials and energies beyond comprehension. Still, these constructs, cosmic strings, Tipler cylinders, rotating universes, demonstrate something profound. Relativity does not forbid time loops. Its equations, when pushed to their extremes, whisper that reality may be capable of bending not only space, but causality itself. The question is not whether mathematics allows it, but whether physics does, whether the real universe tolerates such extravagances or erases them with deeper laws, yet unknown. In the speculative realm of exotic physics, time travel is neither wholly myth nor wholly real. It is a frontier, a place where equations expand possibility, but evidence remains elusive. Cosmic strings may yet be discovered. Exotic matter may one day be engineered. Or perhaps, as Stephen Hawking suspected, the universe itself conspires to prevent paradoxes, enforcing a chronology that mathematics alone cannot. For now, the search continues. The cosmos may yet reveal scars in space-time or strange rotations of geometry that hint at these exotic engines of time. And if it does, humanity will be forced to confront not only the possibility of travel, but the deeper question. If time can be bent into loops, what does it mean to live inside one? The universe, through Einstein's relativity, opened doors to possibilities stranger than fiction. If wormholes were one such door, then cosmic strings, Tipler cylinders, and rotating universes were others, speculative, audacious, and haunting in their implications. To peer into these ideas is to glimpse realities where time itself is no longer linear, but tangled into spirals and loops. Among the most striking of these visions is the Tipler cylinder. Proposed by physicist Frank Tipler in 1974, it imagines an infinitely long, massive cylinder, spinning near the speed of light. The rotation would drag space-time around it, twisting paths into closed time-like curves. A spacecraft navigating these curves could, in theory, emerge in its own past. The mathematics is precise, but the practicality is impossible. An infinitely long cylinder cannot exist in our universe. Even a finite version would demand energies and materials beyond human comprehension, perhaps beyond the cosmos itself. Yet the concept remains important, not as a blueprint, but as proof that relativity permits such strangeness. Even stranger is Gödel's universe, introduced by mathematician Kurt Gödel in 1949. Gödel discovered that Einstein's equations allowed for a cosmos in which the entire universe rotated. In such a universe, closed time-like curves would naturally emerge, allowing journeys into the past without paradox. Yet, Gödel's model did not match our observations of the cosmos. There is no evidence that the universe as a whole spins. Still, his work revealed something profound. Relativity, when stretched to its limits, does not protect chronology. It permits time loops, even if the physical universe does not. Cosmic strings offer yet another pathway. If two such strings existed and moved near light speed past one another, their warped geometries could combine to create closed time-like curves. The mathematics suggests it, though the physics demands conditions so extreme they may never occur. But cosmic strings, unlike Tipler cylinders or Gödel universes, might be real. They could be relics of the early cosmos, scars left from its birth. Astronomers continue to search for their signatures, distortions in the light of distant galaxies, gravitational lensing unlike anything caused by ordinary matter. If found, they would be not only evidence of the universe's infancy, but perhaps the first real material of a time machine. Still, every vision of time loops confronts the same dilemma: paradoxes. Allowing closed time-like curves seems to invite contradictions, the destruction of causality itself. To some, this means that while mathematics permits them, physics does not. Quantum mechanics may intervene, destabilizing such loops before they can form. This is Hawking's chronology protection conjecture, the universe, in his words, making itself safe for historians. But others see the paradoxes not as barriers, but as hints. Perhaps the loops would not destroy causality, but redefine it. Perhaps history would become self-consistent, with every action already woven into the tapestry of time. Or perhaps multiverse branching would resolve contradictions, each loop opening into a new strand of reality. The possibilities are unsettling, but they reveal the depth of the mystery. Time, when bent to its extremes, may not obey the common sense of linear cause and effect. These exotic constructs, Tipler cylinders, Gödel universes, cosmic strings, remain speculative, untested, perhaps forever out of reach. Yet their importance is undeniable. They show that within relativity, the laws of the cosmos do not forbid time loops. They reveal that the universe may be stranger than our lived experience suggests. And they remind us that to dream of time travel is not only to imagine fantasy, but to wrestle with the most extreme edges of physics itself. In the end, whether such constructs exist is less important than what they signify: that our understanding of time is incomplete. The equations whisper of possibilities we cannot yet touch, possibilities that may never be realized, yet still shape our vision of reality. Time may not be the straight arrow we perceive, but a labyrinth of curves and spirals waiting to be mapped. The quantum perspective. If relativity reshaped our view of time on the grand scale, then quantum mechanics unsettled it at the smallest. Here, in the subatomic world, time does not march steadily forward like a clock's hand. Instead, it flickers, hesitates, and sometimes seems to vanish into uncertainty. Where relativity bends the river of time, quantum theory dissolves it into mist. At the heart of quantum mechanics lies uncertainty. Particles do not exist with definite positions and velocities until they are measured. Instead, they hover in a haze of probabilities, occupying many possible states at once. This is superposition, the electron spinning both up and down, the photon traveling through both paths of an experiment simultaneously. Only when observed does the wave of possibilities collapse into a single outcome. This indeterminacy raises profound questions about time. If a particle can exist in multiple states at once, could it also exist in multiple times? If the past and future are only probabilities, then the flow of time itself may not be fixed, but subject to quantum ambiguity. The strangest demonstration of this is the delayed choice experiment. When photons pass through a double slit, they behave like waves, interfering with themselves, unless measured, in which case they behave like particles. But what happens if the decision to measure them is delayed until after they've passed the slits? The result suggests that the act of observation can influence not only the present, but what seems like the past. It is as if reality waits to decide until asked, and in doing so, reshapes history itself. From such puzzles emerges the possibility that time, at the quantum level, is not a simple arrow, but a tapestry of probabilities. The past may not be wholly fixed. The future may not be wholly open. Both may exist as overlapping possibilities, collapsing only when interaction makes them definite. This leads naturally to the many worlds interpretation. First proposed by Hugh Everett in 1957, it argues that every quantum event splits the universe into branches. In one world, the particle lands here. In another, it lands there. Each possibility is real, each world equally valid. Applied to time travel, this interpretation dissolves paradoxes. A traveler who journeys to the past and alters events does not rewrite their own history, but creates a new branch. In one world, the grandfather lives. In another, he does not. Time loops, in this view, become migrations into parallel timelines. The quantum perspective does not hand us a machine, but it offers a new way to think about time. Where relativity stretches and curves it, quantum mechanics fractures it into possibilities. Where entropy gives it direction, quantum theory suggests that direction may not be absolute. If time travel exists, it may not be a return to one fixed past, but a leap into one of many coexisting realities. And so, in the haze of the quantum, the question deepens: is time truly real, or is it only the shadow of deeper processes we do not yet understand? If superposition and the many worlds interpretation fracture time into branching possibilities, then entanglement suggests that time itself may not be local, that what happens here and now can be inseparably linked to events far away, and perhaps even in the future. Entanglement is the quantum bond between particles born together or made to interact. No matter how far they are separated, their states remain correlated. Measure one and the other is instantly defined, even across light years. Einstein called this spooky action at a distance, doubting its reality. Yet experiment after experiment confirms it. Entanglement is not a trick of perception. It is woven into the fabric of reality. But what does this mean for time? In some interpretations, entanglement seems to defy not just space, but causality. A choice made now can appear to influence a measurement that was, in some sense, already determined. This leads into the idea of retrocausality, the possibility that the future can reach back to shape the past. In delayed choice experiments, the act of observation appears to decide outcomes retroactively, as if the universe keeps its options open until forced to choose. If true, then time may not flow one way. Past and future may be entangled, bound in a symmetry that our consciousness only perceives as directional. The implications for time travel are profound. If the future can influence the past on the quantum scale, might there be conditions under which macroscopic systems, perhaps even us, could harness this? Physicists are cautious. Quantum effects are fragile, easily destroyed by noise. But the principle that time's arrow might soften at the smallest scales leaves open the possibility that our experience of linear time is emergent, not fundamental. Modern research pushes these ideas further. Experiments with entangled photons show correlations that defy classical explanation. Quantum computers, built on superposition and entanglement, already process information in ways that blur the line between past calculation and future outcome. Theorists even propose that space-time itself may be built from entanglement, that geometry and gravity are emergent from quantum bonds. If so, then time itself may arise from the fabric of quantum information, and with it, the rules of cause and effect we take for granted. Speculative models suggest that wormholes and entanglement may be linked. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, posits that every entangled pair of particles is connected by a microscopic wormhole. If true, Entanglement would not only tie particles across distance, but also across time, with wormhole-like connections threading the cosmos at the most fundamental level. In such a universe, travel through time might be less a matter of engineering vast machines and more a matter of unlocking the connections already woven into quantum reality. Yet caution persists. No experiment has shown retrocausality in a way that allows information to be sent backward in time. Entanglement correlations cannot transmit signals faster than light. The quantum world teases us with glimpses of time's looseness, but never fully breaks causality. Perhaps this is the universe's way of protecting consistency, allowing strangeness without contradiction. And still, the questions remain. If time at the quantum level is uncertain, if past and future blur in probability, if entanglement binds events across epochs, then our perception of time as a steady river may be only a reflection of scale. For particles, time is mist. For us, it is flow. The truth may be that both are real, coexisting, layered. The quantum perspective does not give us a time machine, but it forces us to reconsider what time is. Not a single arrow, not a rigid fabric, but a spectrum of possibilities, connections, and emergent order. It tells us that time travel, if it exists, will not look like the machines of fiction. It will arise from the strangeness already present, hidden in every particle, every entangled bond, every collapse of probability into actuality. Perhaps the future is already here, waiting to be chosen. Perhaps the past is not gone, but simply another branch of the wave function. And perhaps time itself is not the stage upon which reality unfolds, but one of reality's most delicate illusions, the limits of physics. The human mind has always sought unity, one law, one framework, one grand equation that explains it all. Yet in physics, two great pillars rise side by side, towering but unjoined: relativity and quantum mechanics. Each is magnificent, each is true within its realm, but between them yawns a gulf, and at the heart of that gulf lies time. Einstein's relativity describes a universe smooth and continuous, where space-time bends under the weight of matter and energy. It is a cosmos of curves and warps, of planets following geodesics, of clocks ticking differently under gravity and motion. Time here is geometric, woven into the fabric of space itself. Quantum mechanics, by contrast, lives in the small, the uncertain, the discrete. Here, reality is granular, built of quanta, packets of energy, indivisible units. Probabilities rule, and events flicker in and out of being until measured. Time in quantum theory is not geometry, but a parameter, an external background against which probabilities evolve. The clash is profound. In relativity, space-time is dynamic. It bends, flexes, responds. In quantum mechanics, space-time is rigid, a stage that does not change. Relativity tells us gravity is geometry itself, while quantum mechanics insists gravity must be a force, carried by particles like the hypothetical graviton. Each framework works flawlessly in its domain, but at their intersection, black holes, the Big Bang, the quantum fabric of space-time, they contradict. Consider the singularity at the heart of a black hole. Relativity predicts that space-time curves infinitely, collapsing into a point where time ends. Quantum mechanics recoils. Infinities signal not truth, but breakdown. At the smallest scales, quantum theory demands discreteness, a granularity that relativity refuses to allow. In such places, our laws unravel. We do not yet know what time means there, whether it halts, dissolves, or becomes something altogether different. The search for a deeper theory is the search for quantum gravity. string theory, loop quantum gravity, causal sets, all seek to reconcile the smoothness of relativity with the granularity of quantum mechanics. And at the core of each is the same question: what is time? In some visions, time is emergent, a byproduct of quantum entanglement. In others, time dissolves entirely, replaced by relations between events with no underlying clock. The limits of physics today are not only technological but conceptual. We can describe time as dilation, as entropy, as probability. But unifying these visions remains unfinished. The closer we look, the more fragile our understanding becomes. Time, which feels so certain in daily life, grows uncertain at the foundations of physics. It may be that to truly grasp time travel, or even time itself, we must first heal the rift between relativity and quantum mechanics. For now, we live in the shadow of two great truths that cannot yet be one. To stand at the frontier between relativity and quantum mechanics is to gaze into the heart of our ignorance. Both theories have transformed our vision of the cosmos, yet neither can claim to be complete. The search for a deeper union, quantum gravity, is, at its core, a search for the truth about time. One contender is string theory. Here, the building blocks of reality are not particles, but tiny vibrating strings, each vibration corresponding to a different particle. Gravity, in this picture, emerges naturally, carried by a vibration that corresponds to the graviton. Space-time itself, rather than being fundamental, may arise from the geometry of higher dimensions, curled into scales smaller than atoms. In this view, time could be emergent, an echo of the string's deeper dynamics, not a bedrock entity. Another approach is loop quantum gravity. Where string theory envisions higher dimensions, loop quantum gravity imagines space-time itself as discrete, woven from finite loops. At the Planck scale, space and time break into quanta, indivisible units that form a granular fabric. Continuity is an illusion of scale, much like a smooth beach hides its grains of sand. Time, in this framework, is not universal, but relational. It arises from the interactions of events rather than flowing independently. The most enigmatic clues come from black hole thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes are not purely gravitational abysses, but thermodynamic objects, with entropy proportional to the area of their event horizons. Hawking further revealed that black holes radiate, losing energy until they evaporate. These insights blur the line between geometry, quantum theory, and thermodynamics, suggesting that space-time itself may be built from microscopic degrees of freedom we do not yet understand. If so, then time may be less a flowing river than a bookkeeping of information, a statistical property of the universe's hidden states. Out of these insights grows a new suspicion. Perhaps time is not fundamental. In certain versions of string theory, time emerges from more primitive variables. In loop quantum gravity, it dissolves into networks of relations, meaningful only when matter interacts. Even in black hole physics, time seems to vanish at the singularity, replaced by timeless laws of quantum states. Carlo Rovelli, one of loop quantum gravity's architects, has argued that time is not real in the way we think. It is a convenient approximation, born from deeper, timeless equations. This is where the dream of time travel encounters its sharpest edge. If time is not fundamental, then the very idea of traveling through it becomes suspect. One cannot travel through something that does not exist independently. What may be possible is to navigate the patterns of information, the structures of causality, the emergent order that we call time. A time machine in this sense would not be a vessel sailing a river, but a device manipulating the underlying structure that makes the river appear. And yet, even as physics undermines our everyday concept of time, it reveals its necessity. We experience time, we measure it. Our lives are bound to its flow. Even if time is emergent, it is no less real to us than temperature or pressure, both statistical phenomena that feel tangible despite being products of deeper interactions. The limits of physics today are limits of imagination as much as of technology. Relativity and quantum mechanics each describe a world consistent within itself, but incomplete when joined. The unification that physicists seek will not only reconcile two frameworks, but redefine time itself. Whether it emerges as geometry, as probability, or as information, the discovery will transform our understanding not only of time travel, but of existence. Until then, we live in a universe divided, smooth curves above, quantum flickers below, and between them, a mystery. What truly is time? Time and the human mind. Physics describes time with equations, symmetries, and geometry. But for human beings, time is not an abstract coordinate. It is lived, felt, and remembered. Our experience of time is deeply woven into consciousness itself. To ask about time travel, then, is not only to ask about space-time and relativity, but about memory, perception, and the mind's fragile theater where past and future take shape. The first truth is this: the brain does not perceive time directly. There are no receptors for seconds or hours. Instead, the mind constructs time from change, from rhythm, from sequence. The ticking of a clock, the heartbeat, the shifting of shadows, these are signals that the brain weaves into a story of flow. Without change, time vanishes. In sensory deprivation chambers, or in moments of deep meditation, people report losing track of time, as if the arrow itself had dissolved. Memory anchors the past. Without memory, there is no before. Each recollection stitches together the illusion of continuity, giving the sense that life is a line rather than a series of moments. The future, meanwhile, is shaped by anticipation, prediction, imagination. We project forward, constructing possibilities and fears, weaving a sense of destiny. In this way, the brain inhabits not the present, but a corridor between memory and expectation. This is why time feels elastic. Minutes in boredom stretch like hours. Hours in joy vanish in moments. Trauma freezes time, etching seconds into permanence. Awe expands it, filling instants with infinity. Time, for the mind, is not a universal constant, but a living experience, subjective and mutable. Neuroscience suggests that multiple clocks operate in the brain. Some neurons track milliseconds, governing reflexes and rhythm. Others govern longer intervals, pacing our sense of days. Circadian rhythms, driven by the rotation of the Earth and the chemistry of light-sensitive proteins, tie our inner clocks to the cosmos. Yet none of these clocks measure time as a physicist does. They measure change, order, and sequence, giving rise to the feeling of flow. This leads to an unsettling thought. If time in physics is already suspect, emergent, relative, perhaps illusory, then our human experience of time may be doubly constructed. Not only is it shaped by the laws of the cosmos, but it is filtered through the architecture of the mind. We do not live in time as it is, but in time as we perceive it. The past is memory, the future is imagination, and the present is a fleeting window the brain continually rebuilds. For philosophers, this has long been a central puzzle. Augustine of Hippo, writing in the 5th century, admitted, "What then is time? If no one asks me, I know. If I wish to explain it, I know not. The mind knows time instinctively, yet cannot define it. Modern neuroscience has not fully answered him. It has only shown that time is less an external stream than an internal construction. This construction fuels the longing for time travel. Regret, nostalgia, hope, all arise from memory and imagination. We wish to revisit the past because memory makes it vivid. We wish to leap into the future because imagination makes it possible. The very desire for time travel may be less about physics than about psychology, the human refusal to be bound by loss and mortality. And yet, the mind also hints at possibilities. In dreams, time flows differently. In altered states, minutes stretch into lifetimes. Our inner clocks can be fooled, shifted, reset. If time travel in the physical sense remains uncertain, time travel in the psychological sense is undeniable. Memory transports us backward. Imagination propels us forward. We are already travelers, though within the theater of the mind. The study of time in physics often feels cold, mathematical, precise. Yet when we turn to the human mind, time reveals its most personal and fragile form. For consciousness itself seems to weave time, shaping not only how we experience life, but how we imagine bending or escaping it. Psychological experiments show that our perception of time is astonishingly malleable. In high adrenaline situations, accidents, near misses, moments of terror, people often report that time slows down. Neuroscientists suggest this is not because external events literally change speed, but because the brain records far more detail than usual. The richness of information stretches memory, making seconds feel like minutes. Conversely, when we are bored or deprived of stimulation, the brain records little. The present empties out, and time feels heavy, dragging with each tick of the clock. In states of deep absorption, what psychologists call flow, time can vanish altogether. Artists painting, athletes in motion, musicians performing, all report losing hours without noticing. The brain, focused entirely on the moment, suspends awareness of time's passage. Similarly, meditation and mindfulness practices quiet the narrative mind, reducing the sense of linear flow. Practitioners often describe timelessness as if they had stepped outside the ordinary current of life. Even more mysterious are near-death experiences. Many who survive such events describe life reviews, where memories unfold in rapid succession, or a sense of timelessness where all moments coexist. Whether these are products of brain chemistry under stress or glimpses into deeper truths, they highlight how consciousness can unshackle itself from ordinary time. Neuroscience hints at why. Time perception involves multiple brain regions, the cerebellum for milliseconds, the basal ganglia for rhythms, the hippocampus for ordering events, and the prefrontal cortex for projecting into the future. There is no single time center, but a network stitching together moments into a narrative. Damage these networks, and time fractures. Patients with certain brain injuries lose the ability to sequence events or to estimate durations, living in fragmented presents without coherent pasts or futures. Philosophers and scientists alike wonder if consciousness is the true seat of time. Physics may describe time as geometry or probability, but perhaps what we call the flow of time exists only because the mind builds it. Some even suggest that consciousness itself arises from the brain's constant negotiation of past and future, binding perception into a present moment. In this sense, time and awareness are inseparable. Without the mind, time may not be experienced at all. This opens startling possibilities. If our perception of time is a construct, then perhaps our sense of its linearity is not fundamental, but adaptive. Evolution may have wired us to experience time as forward-moving because it aids survival, learning from the past, predicting the future, acting in the present. But in altered states, dreams, psychedelics, meditations, the construct loosens, revealing other ways the mind can inhabit reality. And so, the yearning for time travel may arise not only from physics, but from psychology. We long to return to lost moments, to undo mistakes, to relive joys, not because the universe invites it, but because memory binds us to the past and regret refuses to release us. We long to leap into the future because imagination paints it vivid, and hope insists on seeing what comes next. In the end, perhaps the greatest time machine is the mind itself. It already travels, revisiting the past through memory and rehearsing the future through imagination. It bends, stretches, and collapses time every day. Physics may one day grant us wormholes or cosmic strings, but the first, most accessible form of time travel has always been within, the strange, shifting theater of human consciousness.